In this lecture, we are working with predicates. Predicates behave similarly to our propositions from the last lecture, but this time they receive input. This input affects whether the predicate will result in true or false. We are also going to work with quantifiers, such as for all and there exists, along with our predicates. These will show that some predicate, such as p of x, might always be true, or only sometimes be true, for any given input passed in as x. So first we'll talk about predicates and describe what a predicate is. Then we'll use the quantifiers for all and there exists to build quantified statements. We will talk about coming up with a counterexample to disprove a quantified statement. We will look at negations of quantified statements. We will look at the common numerical sets, such as the set of all real numbers and the set of integers. And finally, we'll talk about predicates with two variables. Predicates are similar to propositions, except that predicates take an input, and the result will be a proposition that is either true or false based on that input. If we make a statement like x is positive, then whether the statement is true or not depends on what x is. So, it's true if x is 10, and it's false if x is -5. While propositions are usually written with lowercase letters, like p and q, predicates are usually written with uppercase letters in their input variable, like p of x and q of x. In programming terms, think of propositions like our Boolean variables, and think of predicates like defining a function that will return either true or false. Let's say that we want to ask, where is my pizza if the pizza is late? If we just use a simple proposition, we can set it to true or false. But if we want to have something a little bit more sophisticated, we could write a function and pass in the amount of minutes it's been since we ordered the pizza. Inside of the function, it will look at the input variable and return either true or false based on whatever criteria it's set up to work with. If we just want to state the pizza is not late, we can use a proposition. But for a predicate, it would be more like saying, if it's been more than 45 minutes, then yes, the pizza is late. If we were writing this more in discrete math terms, we could write something like, p of x is the predicate, x is greater than 45, and that would return true or false based on what is passed into p of x in place of x. We can also use our logic operators and, or, and not with predicates. So let's say we have two predicates. P of x is the predicate x is even, and q of x is the predicate x ends in 0. If we write p of x and q of x, then this essentially translates to x is even and x ends in 0. If we write p of x or q of x, this will be x is even or x ends in 0. And then the negation of p of x would end up being x is not even. Are these statements true or false? Well, we won't know until we specify the input x. Time for some practice. Let's say p of x is the predicate x is prime. Decide whether plugging in the following values will result in true or false. First, x is 3. Second, x is 9. For p of x is the predicate x is prime, if we plug in 3, this is true, 3 is prime, and if we plug in 9, this is false, 9 is not prime. Sometimes, no matter what you plug into a predicate, it will always come out to the same result, either always true or always false. If this is the case, we can use a symbol that means for all x to specify that for all input values of x, the predicate will evaluate to the same result. On the other hand, if a predicate may be true for some values of x and false for other values of x, we can use a symbol to say there exists some input value x such that the predicate will give some result. The for all symbol looks like an upside down A, and the there exists symbol looks like a backwards E. So when you see upside down A with an X next to it, it would be read as for all X, And if you see a backwards E with an X next to it, it would be read as, there exists some X. Further, when we're making a quantified statement, we also need to specify what the domain is. The domain specifies the set of all possible input values we can use with our predicate. So putting this all together, let's say we have a set named D. D contains the numbers 2, 4, 6, 8, and 10. When we choose some value X to plug into our predicate, X will be selected from the domain D. In this case, we can see that all elements of the domain D are even numbers, so we could say E of X is the predicate X is even, and then we can write out symbolically, for all elements X in the set D, E of X, or our predicate X is even is true. So for our entire quantified statement, we need 1. The quantifier, either for all or there exists. 2. Defining the input variable and what the domain is. And 3. The statement that will be true for all input values of X. Let's say that we changed this around so that not all elements of D were even. So now D is the set 1, 2, 4, 6, 8, and 10. We'll keep the same predicate. E of X is the predicate X is even. And in this case, saying for all X in D, E of X is not valid. Or in other words, saying for all elements in the domain, that element is even. This is not true because now we have a 1 in there. But we could say that there exists an X in D such that X is not even. Or symbolically, we would write, there exists some X in the domain of D such that not E of X, or the negation of E of X. So with this domain and this predicate, what kind of quantified statements are true? Well, we could say, there exists some element X in D such that X is even. We could also say, there exists some element X in D such that X is not even. And the following quantified statements would be false. For all elements X in D, X is even, and for all elements X in D, X is not even. So in order to state for all X in D P of X, it must be true for all input variables. And in order to state there exists some X in D such that P of X, it must be true for at least one input variable. Here's another practice problem. Translate the following into English and specify whether the quantified statement is true or false. So we have for all X in D, P of X, and P of X is the predicate X is negative, and D is the set containing -5, -10, -15, and -20. So writing this as an English statement, we would have for all elements X in D, X is negative. For this domain, this quantified statement is true. Okay, now translate this to English. There exists some input variable D in the domain such that G of D, where G of D is the predicate D is a good boy, and D is the set of all dogs. So as a phrase, this would be, there exists some dog in the set of all dogs, such that the dog D is a good boy. Okay, time to go the other way around. Translate the following into a quantified statement. You must define the domain and the predicate. The statement is, all numbers between 1 and 10 are positive. So, first, will this be for all or there exists? What is the domain? And what is the predicate? So you should end up with, for all X in D, P of X, where the domain D is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and P of X is the predicate, X is greater than 0. Okay, one more for now. Translate the following into a quantified statement. You must define the predicate. So given the domain D equals 1, 1, 2, 3, 5, 8, some numbers are even. As a hint, For your predicate, just write is even in English. We have not yet covered how to specify that an integer is even mathematically. That's for another lesson. You should have written, there exists some x in D such that e of x, where e of x is the predicate, x is even. Now note that a common error starting out is for students to try to write x is even mathematically. They usually write it wrong, so don't even try. For now, for statements like these, just stick to writing it as an English sentence as part of the predicate. We will cover definitions of even and odd numbers in another section. If we have a quantified statement of the form, for all x in D, p of x, if we can find at least one x that makes p of x false, then we can disprove the entire quantified statement with this counterexample. We can only use a counterexample to disprove a statement that specifies for all, but we only need one example to do so. So let's say we have the domain D equals 1, 3, 5, 7, 9, and 10, and we have p of x is the predicate, x is odd, and we have the quantified statement for all x in D, p of x. If we inspect the domain D, we can see that not all elements are odd. 10 isn't. Therefore, we can use 10 as the counterexample to show that the quantified statement for all x in D, p of x, is false. So now you try. Find a counterexample for the following. Given the domain D is 3, 4, 6, and 12, and p of x is the predicate, x squared is even, find a counterexample for all x in D, p of x. This is false for p of 3. P of 3 is going to be 3 squared, which ends up being 9, and that is not even. If we come across a quantified statement that is false, we can say that the negation of that statement is true. So for example, let's say we have the domain D is 1, 2, 4, 6, 8, and 10, and e of x is the predicate, x is even. In this case, not every input x from the domain makes the predicate e of x result to true, so we cannot state that it is true for all elements of x in D. But what do we get if we negate it? Well, if we negate for all x in D, e of x, we are essentially saying it is not true that for all x in D, x is even. This negation comes out to be there exists some x in D such that not e of x. Or, in English, there exists some x in D such that x is not even. Likewise, let's look at a statement that uses there exists. So let's have there exists some x in D such that O of x. We have the domain D is 2, 4, 6, 8, 10, and O of x is the predicate, x is odd. We can see that in the set, none of the elements are odd, they're all even. So what is the negation of this quantified statement? If we negate there exists some x in D such that O of x, we're essentially saying it is not true that there exists some x in D such that x is odd. And so the negation of this will be for all x in D, not O of x, or for all x in D, x is not odd. So to summarize, when we're negating a quantified statement that uses for all and p of x, the negation will be there exists and not p of x. And vice versa, if we are negating a statement that says there exists and p of x, then the negation will be for all and not p of x. Time to practice. Find the negation of the following. 1. There exists some x in D such that p of x. 2. For all x in D, not q of x. The negation of there exists some x in D such that p of x is for all x in D, not p of x. And the negation of for all x in D, not q of x will end up being there exists some x in D, q of x. So a double negation here not q of x, and then not q of x, ends up just being q of x. Throughout this class, we will be working with sets, but it is impossible to list all of the elements of a set, like, say, the set of all numbers. So we have some special symbols to denote common numerical sets. The set of all real numbers includes any type of number you can think of, such as irrational numbers, rational numbers, integers, and so on, but it doesn't include imaginary numbers, such as if you took the square root of -1. The set of all real numbers is represented by an R symbol. A rational number is any number that can be expressed as a fraction, including whole numbers, as they could be written as, for example, 4/1 instead of 4, and fractions that have infinitely repeating decimals, like 1/3. So, for the set of all rational numbers, this is represented by a Q symbol. An integer is a number that can be written without a fractional component. So in other words, integers are whole numbers. The set of all integers includes negative whole numbers, positive whole numbers, and 0. The set is represented by a Z symbol. Natural numbers are thought of as counting numbers, so these do not include any negative numbers, but this will be whole numbers, including 0 and all of the positive numbers. The set of natural numbers is represented by an N symbol. Additionally, we can add a greater than or equal to 0 sign or a plus sign to our set to further restrict it to either being greater than or equal to 0 or positive numbers only. So for example, if you wrote the set Z, or all integers, but also added the plus sign as a superscript, then it would be the set of all integers that are positive, so no 0 and no negative numbers. Finally, let's talk about predicates with multiple variables. We might want to write a quantified statement that includes 2 input variables. So we could write p of x and y is the predicate y plus 1 equals x. When we're writing a quantified statement that contains multiple variables, we're going to have to add an extra quantifier, one for each of the input variables. So for this predicate, we could write for all x in the set of all integers, and there exists a y in the set of integers, such that p of x and y. Or in other words, for all integers x, there exists some integer y, such that y plus 1 equals x. When we have the negation of a quantified statement that includes multiple variables, each part of the statement will be negated. So if we have for all x and z, there exists y and z, p of xy. Each part of this will be negated, so the negation of the whole thing is there exists x and z. For all y and z, not p of xy. Now let's practice. Negate the following quantified statement, and specify whether the negation or the original was true. For all integers a, and for all integers b, p of x, where p of x is the predicate, a plus b is in the set of integers z. Your negation should end up being, there exists some a in z, there exists some b in z, where not p of x. Or in other terms, there exists an integer a and an integer b such that a plus b is not an integer. Now, if we look at these, the original version was true and this other version is false. If we add two integers together, we will always get an integer back. So that was a lot of information. Make sure to practice to gain a better grasp of how predicates and quantified statements work. Next time we will be talking about implications, which are essentially if-then statements. In discrete math, we can write these with either propositions or with predicates.